Good weekend. Any questions? The midterm marks have been posted. The midterm is available for viewing on GradeScope. And the solutions on Yahoo. So take a look at that. The average was just under 65%. So it's a bit low, but not as bad as math. Not that fun. So let me say something that's complicated about this. So some of you, there'll be one question at least where your mark is disappointing. And what do you do when you see a bad mark? What's the process you go through? Anger, right? Because the test was too hard or too long. Excuse me, right? Then what? After anger.
Stand in the shower for 2 hours.
Weeping. That's too long to stand in the shower. Unless you have an unlimited supply of hot water. Okay, all right. And you weep for a while, and then you turn on and weep. And then what do you do after that? At some point, maybe what you do is you just try to pretend it didn't happen. And that's, I don't want you to do that. Okay, so the midterm is, I want you to think of it as formative assessment. So yeah, we got a grade, and it's 30% of your final grade. But it's not the end of the course. What the midterm did was assess certain learning goals of the course. There were 8 questions, roughly 8 course learning goals. And if you got a bad mark on one of them, it means you just haven't achieved that learning goal yet. But there's still time to do that. Now, when we get to the final is formative assessment. There's nothing after the final, right? So by then, you want to know those learning goals. Okay, so to encourage that behavior, so you can do all the other things. This is normal human reaction to things, anger, grief. But then when you get to the denial stage, stop. I guess one of the I skipped over is the arguing stage, or what is it? The bargaining stage, yes. And so you actually have a bargaining stage, but don't treat it that way. If you see an error in the marking, then there's a process of question marks. But anyway, when you get to the denial, stop. And here's what I'm going to give you an incentive for this. So all of these learning goals will be assessed in some form or another on the final. Probably with individual questions, but sometimes it'll be a group of questions. So for example, there'll be a question in the final that requires reading assembly language. There'll probably be a question on reference counting, probably a question on dynamic allocation, all these things, okay? So what we'll do is we're going to take each of those questions, the score you get on the final, for that learning goal. We'll update your midterm mark for that question, for that learning goal, to be the maximum of 80% of the final and what you got in the midterm. Okay, so you can improve for any question just by achieving that learning goal and being able to demonstrate it on the final. You can raise that mark up 80%. Okay, so everybody today, that's an A, right? So at this point, everyone can still get an A in the course. That makes sense. It's complicated. We're close to explanation of the outside. The main thing I want you to take away is after you do all those things about the midterm, say, well, okay, what's all right? I mean, it's not the end of the world because I can change those. Questions about that? So here's the math question. So let's say on reference counting, you only got 20% on the midterm, and not so optimistically, you only got 70%. Well, 70% is not bad, right, on the final for that question. What is your final mark of the midterm question? Well, it's max of 20%, comma, 80% times 70%. 0.8 times 0.7. Whatever that is, I don't know. Right, 65%? So it's 80% of whatever you get. But you can do better than 70%. Yeah, okay. So any other questions? All right, so we're continuing talking about how viruses attack programs using the buffer overflow stack smash exploit. It's the most common exploit. It's actually relatively hard to mount today, but still not impossible. We'll talk later about the reasons why it's hard and what virus writers do to get around countermeasures put in place. A virus is a string. It's some input to a program. This is the input that caused a perfectly innocent program to print out hello from Robert Morris and then go into the infinite loop. The way that it does, so this is a file, it's a hex dump of the file. So it's just showing the content of the file as a sequence of numbers, of hexadecimal numbers. So the first 2020 is the first 2 bytes of the file. And when you go again, the 2e is the last byte of the file, all in hex. Okay? And this becomes input to a program. It becomes a string that the program is copying from into a buffer, into an array that's on the stack. And it overflows that array because the array is only 10 bytes long, but this is much bigger than 10 bytes. And it starts to write things in memory going down like this. And one of the things it does is it writes a number over top of the return address. So that used to point to, in this case, it was a statement in main. That's where the program was going to jump to, this procedure was going to jump to at the very end of the procedure when it does something like this, load some offset from the stack pointer, if that's 25, whatever, 24, whatever it may be, into R6, and then jump R6. This string, when it overflows this, it smashes this to be a pointer into a lower spot on the stack, and then the file contains a set of no-op instructions, which here are, this is x86, so it's opcode, the instruction 90 in hex is a no-op, and then the virus code, which is in red. And you can even see the part of the string that prints out is hello, Robert Morris. So what happens when this procedure returns is it executes these 2 instructions, jumps somewhere in here, wherever that's pointing, and starts executing. It thinks it returned to the procedure, but it didn't. It returned to the virus. And it comes down here, and then executes this program. Okay, that's what we covered last time. So we talked a little bit about Robert Morris. I mentioned at the end of the class that he was a grad student. He was a grad student at Cornell in the 80s. And he had an idea, at least as he tells it, an innocent idea, to count the total number of machines in the internet. And he thought, well, what I'll do is because he knew how to do this, I'll send out a little virus that'll infect every program on the internet and just send back a message to me so that I can count how many unique machines there are on the internet. And this is the 80s, the internet's fairly small. This is before Facebook. Even before email, really. It sort of existed, but not quite. And this is a piece of this is the virus itself. So what this virus does is run a shell. So this is command line. So he sent a virus so he could run a command line, and then to the command line, part of the virus string was input to the command line. And there's some commands that had the command line just get its IP address, send a quick message back to Cornell, his machine, and then reproduce itself. And he knew that if he wasn't careful, this thing would go wild. So he had the virus, when it attacked the machine, store a special file that indicates the machine had been attacked. And almost all the time, when he saw that file, the virus wouldn't reproduce, it would just die. But he also knew that sysadmins are smart, and that somebody might figure out, before the virus had completed its task, that all you have to do is place this file on a machine, and it's inoculated. It can't be infected. And so he said, well, every now and then, I'll have the virus reproduce, even if the file's there, as a countermeasure. So with some probability, and I don't remember, it probably never knew, what that probability was, relatively small. And that was his undoing. No one ever would have known about this if it wasn't for the fact that shortly after he released the virus, the entire internet stopped working. And it stopped working because every single machine, guys, every single machine was constantly being infected by this virus. And you might imagine, so this is the first time that a virus had attacked the internet on this scale. So people hadn't figured out ways to deal with it. And you might imagine it's kind of difficult to remove the virus from a machine if the virus is immediately reinfected. So what they actually had to do was they had to take the internet apart, isolate everybody from it, and then remove the virus from that area, and then reconnect it to the internet. And there's something fascinating, I think, about this word virus. Because, so, you know, in computer science, we co-opt words from everywhere, and we, you know, like bug, for example. You know what the word bug is? It was a real bug. It got fried in the computer and caused, but usually, when we co-opt a word, it's, you know, it's sort of unfair. We change the meaning of it. But actually, in this case, everything I've said about this is very similar to a biological virus. So biological viruses are nucleic acids. So they're little pieces of RNA or DNA, you know, wrapped in a protein, wrapped in fat or something like this. Right? What is nucleic acid? It's a program. It's a biological program. And these viruses do nothing until they infect a cell, and they utilize the cell to reproduce. That's the purpose. And sometimes they do this by splicing their DNA or RNA into the host DNA so they become a part of you. So this is like the way HIV works, or herpes. And sometimes what they do is they just use the cell's mechanisms to reproduce themselves. And actually, if they just did that, and they just made lots of copies of themselves, you know, who cares? It wouldn't make you sick. But the one thing that is bad about what viruses do is in order to get out, to spread outside the cell, they usually kill the cell. And so it's this, you know, mistake sort of in what the viruses do that requires that the immune system build up a way to attack them. And, you know, when you have viruses spreading in a population of animals or humans, you know, what do? We isolate them so that the virus can't spread until we can find a way to inoculate machines with the virus. So it's actually very similar, and I think this, you know, sort of a thought about this is that every really complicated system is vulnerable to this sort of thing. So probably viruses are, even though it's exploiting something really stupid in C, as we talked about in the array overflow, they're probably just an inherent part of complexity. Is that this is just, you know, the evolution finding little sort of bugs, little ways to exploit very complicated programs with humans or other animals. Anyway, this is Morris's virus. That's the attack string. So the virus is at the end. The zeros are the no-ops. Oh, I should go back. This is in the VAX machine code. So this was attacking VAX computers, which at the time were the main computers on the internet. If you go to the computer museum, you can see the virus. That's a floppy disk. It's like in an isolation chamber. More recently, this isn't super recent, but yeah, you know. Is that before you were born? Just barely around when you were born. You were born in 2000. So when you were 1 or so, there was a virus that caused fairly widespread damage, but I'm mentioning it because you can see, by looking at the virus, how very similar it is to what I've talked about. Is that, so that is the attack string. It's a URL. The virus was infected Microsoft's web browser, which had an overflow bug while it was parsing the URL. And what the virus did was, it infected machines and then lay dormant for a certain period of time. And then at a certain point, a message popped up and it said something like, it's the second line. Hello, welcome to forum.com hacked by Chinese. Now, there's actually no evidence that anyone Chinese was associated with this. Just, you know, that's either a racial slur or something else. And then it set another timer at which time it was to launch a denial of service attack on whitehouse.gov, which is the U.S. president's white webpage. And this is the kind of thing that viruses do. So, virus writers don't write viruses to display a cute message on your computer. They do it either to cause damage or usually to extract money from people. And so the goal of the virus usually is to turn the infected machine into a zombie. Something that the virus writer can control to do things without the owner of the computer knowing. Guys? So if your machine is infected, you might not know, but your machine might be ready to do something like a denial of service attack. So distributed denial of service attacks are designed to take down a website by sending messages that are malformed TCP messages to a website from many different places in the internet. That when the machine receives it, it causes it to go into sort of a slow mode of executing for a period of time. And so if it gets lots of these, then it spends all of its time just dealing with these messages. Does this make sense? So service is denied because it's being inundated by these messages coming in from everywhere, and that's hard to stop because they're coming in from everywhere. And the virus writer is sort of not, their hands are clean because the attack's not being launched from computers they own. A similar thing happens, so you've all received phishing emails, right? What's a phishing email? Explain.
It's like a scam email.
What's the key feature of this scam phishing email? Yeah.
Can I get your information?
Yeah, how? There's a link. So they have a link that looks like it's to your bank or to your Twitter account or something like that. But if you open it up, you'll see it's a different URL. Now, it might surprise you that URL might be on your computer, because often the way this attack works is that they infect machines, and then those machines launch web servers, and they then host a page that looks like your bank or whatever it is, so that they can get the victim's username and password. And as soon as that happens, one scenario that plays out, there was a study of this some time ago where a researcher actually set up a sting operation, got permission from UCSD, got permission from the FBI to use some real money and see what would happen, and they trace what would happen. And here's what happened: is that the money, as soon as this website, this zombie machine, which is not traceable to the attacker, in these cases it was Russian organized crime, it sends the username and password to another machine. That machine takes the money, initiates a wire transfer to a bank. There's the person in the city where the bank has a branch receives a text message. This person responded to an ad saying, earn $50 an hour really quick. Tear off the little tab and say, well, we can send you a text message. What you need to do is go into the bank, and there'll be a package for you. You take the package, put a stamp on it, write this address on it, and put it in the mail. And that whole that whole sequence of things took about 20 minutes. So within 20 minutes of you clicking on the phishing thing, all your money is gone, and it's untraceable. It's virtually. So that's what viruses are doing. I mean, they're trying to, it's a crime, and it's serious crime. And so it's obviously very important to deal with it. In this case, actually, they had to change the IP address of whitehouse.gov, because it actually hard-coded the IP address, not the domain name, to prevent that attack. So in the assignment this week, you're going to write a virus and attack a server that we're going to place on the internet, and your goal will be to get a shell to execute on that server so that you can send the server arbitrary commands like delete all the files. Okay. To do this, we need to give the SM213 a little bit more power. So we're giving it the power to perform 3 system calls. So these system calls are listed at the bottom. A system call that will read data from standard in, which would be the keyboard or from the network. Write data to standard out, so input and output. And then finally exec a program, so run a program. And the program you're going to run is the shell. So if you run the shell, then you can type commands into it, and it will be just like that at the terminal. Does this make sense? So let me show you how this would work. So Robert has written a virus that will attack the program on Linux that launches very much like Morris's virus. So where is this in here? That's the virus. You'll see what it does is at the very bottom, there's a syscall. The syscall is a system call. The system call that executes is the exact system call, and it provides the input to it is /bit/sa, which is the shell program. Then there's a program here that produces an attack string. That's the attack string, so you'll see the 90s are the no-ops, and then the virus, the star means it's repeated any time, and then there's the virus. So that's this part right here. Are these instructions to the machine? Oh, exit this one number. And then there's a program with the vulnerability that has this overflow problem. So I can do that. It copies from standard input into a buffer and prints out the result. Another way to do this is this. But now, if I just do this. So there's a couple of things here. One, I'm executing the program that has the bug. 2 is that I'm executing it without environment variables because it turned out that this bug's not using the stack. It doesn't matter. It's like it wouldn't work if we did this part. So the real attacker wouldn't worry about that. They'd get around it. And then what's being piped into it is, so cat just takes a file and display and sends it to standard input. So it cats 2 things. It first cats the payload string, which has the virus in it, which infects the program, and the program now will be running the shell. And then it cats again from standard input. So now if this works, I should be able to type things, and the shell program that's running as the result of the virus then will execute this command. Okay, so it printed out this weird thing as it did, but now it's running the shell. So if I type ls, for example, right, I can run any program now. So I can run a program that will send a message to another machine. I could, do this. Don't do that. Delete all the files. I could attempt to become root if I want to try to guess the root password and then take control of the machine. Here it's running as me, but it has access to all my files. Okay, so you're going to do, does that make sense? Any questions? Everything. It's me now. This is a terminal. I mean, it's actually the course account. Oh yes, yeah, that one. Yeah, start over. Just trying to get to the right directory. Yeah, I wanted to show you a little bit while I do this. What assignment are you working on right now? 6, right? That's all your marks. So if you could do this, right, if I had a program that was running with the course account privilege, and you could send it this string, so it's connected to the internet, you would now be me. And from your computer, you could go do whatever you want with grades. So it's bad. This is really, really bad. We don't want to allow this to happen. Well, it all depends. I mean, you know, it's bad for society. It's bad for the victims. Of course, crime is always good for somebody. So, as I said, you're going to do this in the lab. Here's an example of a SN213 program that's been augmented. We've added this new thing, sys $0. Sys $0 is print. Here's the input. This stuff is input, so this will read as input the standard damage in this string. So when you do the lab, you're going to do this in a set of steps. So start with something simple. You'll write something that will launch the shell, and then translate that into SN213 binary. Then we'll help you create an attack string for it with some infrastructure that's provided, and then you can run it locally, get it to work. You'll be doing this with a special version of the simulator that has this syscall instruction added. And once you get it to work for bonus, we'll set up, well actually, so this is in a sense something that's called a honeypot. So this is one way that, one countermeasure to viruses is to set up machines that we know have a vulnerability, or may have a vulnerability, and monitor them to see when they get infected. So it's like honeypot growing bears, what gets infected honeypots. So we'll have this server that's available for you to hack into. It will not have the grades. Okay, it will be in an account that there's no harm you can do, but that's only because we've set it up carefully that way. Okay, so it should be a lot of fun. It's not easy. The goal here of all of this really is to help you understand the stack better, but also to introduce you to computer security. So let's just say a few words about this now. So this is bad, and we don't want to let this happen. So one way we can prevent this from happening, this particular attack, is to use a different language that did the radar checking. So that's a good idea. Unfortunately, C and C++ don't have radar checking, and most programs that and they're the base of security. So, and as I said, even if we did that, this is one particular attack, I believe but can't prove that, as I said, is that viruses are a fundamental, unavoidable feature of complexity. So someone who's sufficiently motivated and sufficiently smart will probably figure out how to infect anything. But in any case, that would solve this problem, but we can't do it. So faced with that, because it's just impractical and impossible to force people to rewrite all these programs in a different language. What else can you do? So I want you to think about the first question here is, we drew the stack, we implemented the stack like this, where it grows up. That was an artifact of historic artifact, some weird thing about in the early days where the heap grew down and the stack grew up, and they hoped they wouldn't meet in the middle. We don't have to do that anymore. We could have the stack grow down. So it could be like this. Where that is this one, right? So here's Bob. And then the other one's above. Name. So discuss with each other for a moment. Whether that helps at all. Okay, so raise your hand if you think you can see a way that this actually might help.
Because right now, like, when you grow this acronym, you might overwrite the internet address of the one below it. So
Yeah.
have it going
So
down.
if I change this picture, where's the, somebody find the erase. Like, if I put the return address at the very top of the activation string, then anything that overflows, whether it's an, because you have to worry about arguments just like local variables, anything that overflows is going to overflow going down like that, which in this picture is up here. So what's down here below this frame? That's the unallocated part of the stack. That's free memory. You can write there all you want. Who cares? Now, you will smash other local variables, but what you won't get to do is smash the return address. So it looks like we solved the problem. Did everybody see that? So sort of the problem here is that when you overflow, you're writing over top of the allocated part of the stack. And if we just flip it around, now you're going to just overflow the unallocated part of the stack. It's not a problem. So why do you think this doesn't solve the problem?
What if the attacker knows you're doing that?
Yeah, so what if the attacker knows I'm doing that? The attacker doesn't get to control anything other than the input to my program. They can't force me to make a bug that I haven't made. They're just exploiting the bugs that I haven't made. Yes, exactly. So remember that C does not check for overflow, and it also doesn't check for underflow. And it seems surprising that it's just as easy to trigger an underflow as it is an overflow. And it actually has to do with the way programs do pointer arithmetic in those loops. And so you can trick them to going in reverse. And so it eliminates many possible vectors, but there's so many bugs like this that it's relatively easy, and every big complicated program can find a bug where instead of going overflowing this way, you start to overflow in the backwards code. Okay, so that doesn't really help. But there are some things that do help, and I'm going to mention 3 of them that list on the slide. So the first one is that it is possible in modern, well, it's been possible for a very long time in operating systems using virtual memory to designate certain properties of regions of memory that will restrict the kinds of accesses that can occur, and that's checked by hardware. So you can mark a region of memory as being, for example, read-only. And if a section of memory is read-only, any attempt to store values in that region of memory will generate a hardware trap, a protection violation, and the program will crash. You can also designate a region of memory as no execute. So if a region of memory is designated as no execute, any attempt to load an instruction from there, to jump to an address in that range, will cause a hardware fault. So all modern stacks are protected using no execute. So it is not, if you jump to code on the stack, your program will immediately crash. It is not possible, if you mark the stack no execute, to execute code that's on the stack. And that's where the virus is. Okay. So that's the first thing. The second thing, well, which is the bottom line, is that you remember that it's, what we need to do here is to guess a number that's somewhere in this range. So basically we have to know the stack address. I, as the attacker, have to know the stack address on your computer. And it used to be that this was deterministic. You know, Linux, Mac, they all choose the same address for the starting stack. So it made the job easy. I just run program on my machine, look at what the stack address is, and then I would assume that it's going to be roughly the same on your machine. And remember, I don't have to get it exactly right because I've got an obsolete little cushion, you know, small errors. But really big errors, like hundreds of megabytes apart, I can't deal with this technique. So all modern systems, what they do is when they start the program, they choose a random address for the stack. So every time you run a program, it's picking another random location for the stack. So it makes it very hard to guess the stack address. The third and final thing that I'm going to talk about is something called stack protection using canaries. And so you'll notice, like we have, here's the return address, and here's the thing, you know, the buff. In order for the attack string to write over the return address, it has to write over everything before it. So if we put something here at canary, which is a number that's secret, that the attacker doesn't get to know, it's private to me, to my code. And then in the jump, before I do this, I'll load the canary and check it. And if this number has changed, then I don't use the return address. And the only way the attacker can change the return address is to write over top of this number. And the only way it can do it without me protecting it is to know what the number is. So the attacker now has to attack it much harder because they have to get a memory leak, an information leak from my program to find out what the canary is in my machine. Any questions about these three things? So, viruses are impossible, right? I've just described three things. Any one of them would seem to make the attack impossible. Okay. But turns out that the attacker doesn't have to write a program here. What it can do is using something called return-oriented programming. It can just provide parameters, because remember, parameters are stored in the stack, it's data, and then an address that points into legitimate code in your program. For example, libc. Libc is the C library, it has everything in it, read, write files, send messages, absolutely everything. Anything that you would want to do as a virus, the code already exists. And if you can control the parameters, it's just as good as having the code. a little bit harder to do that, but that's what most modern viruses do now. How do you know the stack address? That is definitely a problem. You can mount this attack also in the heap, and you'll see why that is in the next section of the course. So if you have an object-oriented programming, or if you have function pointers, as we'll talk about, in any location in memory, not just the stack, you can mount this attack there as well. And data leaks are, it's hard to get, it's impossible to guess the canary in a well-engineered system, but it's sometimes quite easy to make a program to do a kind of overflow that reveals the canary, and then use that information as the next rank of the attack. Okay. So we haven't solved the problem. Probably will never solve the problem. It's an arms race. Extremely important, so that the amount of money that goes into preventative measures and that's lost to cybercrime over years is in the tens of billions of dollars. It is, I mentioned when we talked about rate overflow, I said this was the biggest mistake, most costly mistake humans have ever made, except for war, or something like that, and that of course was a joke, but it is a very costly issue, and it's very important because you can see that what attackers are able to do when so much of society is based upon the correct execution of code and on keeping information close to private, and so on. We have to be sure that we're on top of this. If you're interested, so Robert runs as a club, and they meet on Tuesdays at 6:30 in Street Villa, and he welcomes you to come join the club. And what they do is they go into these competitions where they're given a hacking challenge to infect something, and then they have to figure out how to do it. So you get to do all the fun things that hackers do, but in a very completely above board way. Do that rather than a life of crime. All right. So again, the main goal here with all this stuff is to help you understand the stack, and we talked about the stack. And here's a summary of the things we talked about the stack. Any questions? So we're going to move to the last section of the first part of the course. Which is on dynamic control flow. So, we looked at static and dynamic data. We looked at static control flow. And now we're going to look at dynamic control flow. And this shows up in with two different mechanisms. One that you're very familiar with, which is polymorphism, subtyping in Java and all other C++ and all other object-oriented languages. And then the other one is using function pointers, which is a different technique, but they achieve essentially the same goal. And we'll talk about both. Okay, so we first C is not object-oriented, right? So all of the procedure calls in C are like this. They're like the static calls in Java. Right? It's like when I say foo or ping, it's just ping. It's just one ping. And the compiler knows the address of ping because it compiled ping, so it knows what ping is in memory, and that just becomes an absolute jump to a constant. This is what we talked about. That's a static jump. But if you ever have a jump where when the compile procedure call or a jump, when the compiler does not know the address that you're jumping to, that's a dynamic jump. Okay? And let's look at this polymorphic dispatch thing that you're all very familiar with. So I have two classes, A and B. B is a subtype of A. So instances of B are substitutable into code that has variables of type A. Right? So I can have a actual type of B in a variable whose parent type is A. A implements ping and pong. B implements ping and whip. So it's overriding ping. So there are two implementations of ping in this program, one in the class A, one in the class B. And if I write a piece of code here, foo, that has a variable whose apparent type is A, and then I use A to call ping, which of those two pings is called? depends upon the value of that variable A. And that's illustrated here by two calls to foo. I can call foo with an A, or I can call foo with a B. In the first call to foo, this one's called. And the second call to foo, this one's called. So when the compiler generates code for that line, it cannot be an absolute jump. It doesn't know where to jump to. It has to use dynamic information. What it doesn't know, the value of A, and in fact the type of A, in order to know where to jump to. So this is implemented. So what we're going to do now is we're going to look at, obviously, we're going to get started on this and then continue the rest of the week. We're going to look at how polymorphic dispatch is implemented. And essentially what I'm doing is showing you how C++ does this. Java will do it in an analogous way, but it's Java, so it's slightly different. And it goes like this. It's that every object, so here I have two variables, we'll say A and B, both pointing to an object. This was new A.